Hello everyone and welcome to Control and Estimation Tutorials. This is the second part of the tutorial series on particle filters. In this tutorial part, we derived the particle filter algorithm from scratch. The second tutorial part that you're currently watching is a direct sequel of the first tutorial part. In the first tutorial part, whose link will be provided in the description below this video tutorial, we defined the particle filter estimation problem and we explained important statistics and dynamical systems theory concepts that you need to know in order to understand particle filters. In the third tutorial part, that will be the direct sequel of this tutorial, we will explain how to implement the particle filter algorithm in Python from scratch. Also, we will explain how to generate this amazing animation illustrating the behavior and performance of a particle filter. In this animation, the red circle is the true state of a dynamical system and blue circles are particles generated by particle filter that estimate and track the true state of the system. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot! Here's a brief outline of this video tutorial. First, we will briefly revise the problem formulation of particle filters. After that, we will explain the basic results from statistics and probability that you need to know in order to understand and to derive the particle filter, and after that, we will derive the particle filter algorithm. Okay, let's start with explanations. As explained in the first tutorial part, for presentation clarity and not to blur the main ideas of particle filters with too many control theory details, we develop a particle filter for the simplest possible case. That is, we consider a linear state space model given by this equation. Over here, xk is the state vector at the discrete time instant k, uk minus 1 is the control input vector at the time instant k minus 1, wk minus 1 is the process disturbance vector that is also known as process noise vector, yk is the observed output vector at the time instant k, vk is the measurement noise vector, and a, b, and c are the system matrices. In the first tutorial part, we explained that the main goal of particle filters is to recursively approximate the state posterior probability density function denoted like this. In this notation, y0 until k and u0 until k minus 1 denote the sets of inputs and outputs. The sets are defined over here. In the particle filter and robotics literature, the posterior density is also called the filtering density or filtering distribution. Another name for this density is the marginal density or marginal distribution. Here, keep in mind that some researchers call this density, denoted like this, as the posterior density. This density will be formally introduced later on in this tutorial, and they refer to our original posterior density, given over here, as the filtering density or as the marginal density. However, we will not follow this naming convention. We refer to this density as the posterior density, and we refer to this density as the smoothing density. This is mainly because the density, denoted like this, takes the complete state sequence into account. And this fact means that estimates are actually smoothed. At the time instant k, the particle filter computes the set of particles denoted like this. A particle with the index of I consists of this tuple where xki is the state sample and wki is the importance weight. The set of particles approximates the posterior distribution like this, as a sum where the sum goes from 1 to n, and this is a weighted sum. Here, delta is the Dirac delta function that is shifted and centered at the particular sample xki. The particle filter design problem is to design an update rule or update functions for particles that will update the particles from the time step k-1 to the time step k. That is, we search for an update rule denoted by this right arrow over here that will update the weights and that will update the state samples. Here, the update rule should incorporate the observed output, yk, the control input, uk-1, and our state space model, as well as the state transition probability and the measurement probability. We introduced the state transition probability and measurement probability in the first tutorial part. Once we have this approximation of the posterior distribution, that is, once we compute these weights and the samples, we can actually approximate the mean and the variance of the estimate as well as any statistics such as higher order moments or confidence intervals. To develop the particle filter algorithm, it's important to know the basic rules of probability and the Bayes theorem. Here, we briefly revise the main results from the probability theory you need to know in order to understand the derivation of the particle filter algorithm. In that context, let this notation be an arbitrary conditional probability density function where z1 and z2 are two vectors. Then, we have the following rule. From this equation, we can obtain this equation. On the other hand, we can also write the last equation like this. Now, by combining 8 and 9, we obtain the equation number 10, and from the equation number 10, we finally obtain the equation number 11. This equation represents the mathematical formulation of the Bayes theorem or the Bayes rule. Although it looks simple, this is one of the most important and fundamental results in statistics and probability. In the context of Bayesian estimation, we want to infer statistics or an estimate of the vector z1 from the observation z2. This density, given over here and over here, is called the posterior, and we want to compute this density. This density over here is called the likelihood. This density over here is called the prior density, and this density over here in the denominator is called the marginal density. Usually the marginal density is not important and it serves as a normalizing factor. Consequently, the Bayes rule can be written like this. How do we go from here to here? Well, we simply ignore this constant, and instead of this constant, we add this normalizing constant called gamma. The Bayes rule can also be expanded to the cases of 3 or more vectors. For example, if we would have 3 vectors, z1, z2, and z3, the Bayes rule takes this form, given by this equation. Or it can be also written in this normalized form. Okay, after revising the basics of statistics and probability, let's continue with the derivation of the particle filter algorithm. We start from the probability density function that takes into account all the states starting from the initial state x0 and ending at the state xk. This probability density function is denoted like this, where x0 until k, y0 until k, and u0 until k-1 are sets defined over here. This density takes into account the complete state sequence, x0, x1, x2, and until xk. That is, the complete state sequence is seen as a random variable or augmented random vector that we want to estimate. By knowing the mathematical form of this density, we can easily derive the posterior distribution. This density is often called the smoothing density. The particle filter is derived by first considering the expectation involving the smoothing density, and this expectation is given by this equation. Over here, beta is a nonlinear function of the state sequence, E is the expectation operator, this set S tilde is the state support or domain of the smoothed posterior density. This equation represents the expectation of the vector function beta of the state sequence x0 until k computed under the assumption that the state sequence is distributed according to the posterior smoothed density denoted like this. Note here that x0 until k is actually defined as a set over here. However, we are also using x0 until k as a variable. This is a slight abuse of notation that is necessary in order to ease the notation complexity in this tutorial and to make the tutorial as clear as possible. You can actually think of x0 until k as a vector that is formed by stacking or augmenting the states x0, x1, x2 until xk on top of each other. This equation is the most important equation for us. The main purpose of the estimation process is to compute an approximation of the smoothed posterior density that will enable us to compute this integral. Namely, if we would know the smoothed posterior density, then we would be able to, at least in theory, approximate any statistics of the smoothed posterior state estimate. For example, if you want to compute the mean of the estimated state sequence, then beta will be simply equal to x0 until k. However, the issue over here is that we don't know the smoothed posterior density, and we cannot compute or approximate this expectation integral. Here comes the first remedy for this problem. We will actually need several remedies, however, let's start from the first one. The remedy is to use the importance sampling method. In our previous tutorial, given here, we explained the basics of the importance sampling. I will post a link to this tutorial in the description below this video. The main idea of the importance sampling is to select a new density or a function that's usually denoted like this. This function is called the proposal density or the importance density, and to approximate our original expectation integral, given by this equation, as a finite sum given over here. Over here, x0 until k with index I is a sample of the state sequence sampled from the smoothed proposal density denoted like this, and the weight is defined like this. In the general form, the weight is actually defined like this, where in the numerator we have the smoothed posterior, and in the denominator we have the smoothed importance density or the smoothed proposal density. What did we achieve with this strategy? First of all, from here you can notice that we did not use the unknown smoothed posterior distribution to generate the state sequence samples. We generated the state sequence samples from the smoothed proposal distribution with the density denoted by Q. We can generate these samples since we have complete freedom to select the proposal density. So one part of the issue is resolved. However, the unknown smoothed posterior is used to compute the weights, and you can see this from this equation and from this equation. And that's the issue. If we can somehow compute the weights without explicitly using the smoothed posterior distribution, then we can approximate the original expectation without using the smoothed posterior distribution. From this fact, we conclude that the key to the computation of the expectation is to compute these weights without explicitly computing the smoothed posterior density. That is, without explicit knowledge of the smoothed posterior density. In the sequel, we will show that this is indeed possible. To summarize, the main idea of the particle filter derivation is to derive the recursive equation for the weight wk tilde. Wk tilde is given by this equation. From the recursive equation for the weight wk tilde of the smoothed posterior density, we will be able to derive the recursive equation for the importance weight wk of the original posterior density, that is, the posterior density denoted like this. Let us now start with the derivation of the recursive relation for wk tilde. We can formally write the smoothing density like this. What did I do over here? I took this output sequence and I decomposed this output sequence like this. The first part is output at the time instant k, and the second part is the output sequence starting from the time instant 0 and ending at the time instant k minus 1. Then, by using base rule, we have this. First of all, we use this equation, and then we apply the base rule to this part over here. And as the result, we obtain this. Here, gamma is the normalization factor explained previously. Next, since the state space model is a Markov state space model, we can observe that this density can be represented like this. That is, the density only depends on yk and xk. This is the direct consequence of the form of the output equation of the state space model. Let's look into our state space model. Here it is, and here's the output equation. We can see that the output equation only depends on xk and this noise term vk. Consequently, this density can be written like this. Now, this density over here is the measurement probability density function that we explained in the first tutorial part. Next, let's substitute this equation in this equation, and as the result we obtain this equation. Next, let's transform this density. The idea over here is to write this density like this. How did I obtain this form? Well, I took this state sequence and I separated this state sequence into two parts. The first part is actually the state at the time instant k, and the second part is a state sequence starting from 0 and ending at k minus 1. Next, we can write this density like this. How did we obtain this form? Well, we use the simple probability rule. As the result, we obtained this form over here. Next, since the state space model is Markov, this probability density can be written like this. And this is a very important simplification. It's very important that you understand this step. This is because of the structure of the state equation given by the equation 1. Here's our state equation. We can observe that the state at the time instant k only depends on the state at the time instant k minus 1, input at the time instant k minus 1, and the process noise vector at the time instant k minus 1. Due to this, we can establish this simplification. This density over here is actually the state transition density of the state space model introduced in the first tutorial part. And this is very important to keep in mind. This is the state transition density of the state equation. We simplified this density by using this equation. Next, let's simplify this density. We can observe that this density depends on the input sequence starting at the time instant 0 and ending at the time instant k minus 1. However, over here we can see that we have a state sequence, and the last state in this state sequence is the state at the time instant k minus 1. Now, the issue over here is that the state at the time instant k minus 1 cannot depend on the input at the time instant k minus 1. This is the direct consequence of our state space model. Namely, from the state equation, we can observe that the state at the time instant k should depend on the state at the time instant k minus 1. And if we shift the index in the past for one time step, we can observe that the state at the time instant k minus 1 depends on the input at the time instant k minus 2. And this is a very important observation that helps us to simplify the density. And here is the simplification. Here it is. This density over here can actually be written like this. And notice the difference. We can see here that the input starts at 0 and ends at k minus 1. However, here the input starts at 0 and ends at k minus 2. Now, by substituting the equation 27, that is the first simplification, and this second simplification in our original equation given over here, we finally obtain this form. Next, let's substitute this form in our original equation, that is in equation given by the index 25 in this equation. As the result, we finally obtain this equation. This expression is very important since it establishes a recursive relation for the probability density. Here it is. This is the smoothed probability density. Namely, we can observe that the smoothed probability density depends on its previous value at the time instant k minus 1, and here's the previous value. Then it depends on the measurement density. Then it depends on the state transition probability. And this is a very important recursive equation that will enable us to derive the equation for the importance weights. Next, we need to derive a recursive equation for the smoothed proposal density, that is also known as the smoothed importance density. Again, we start from the general form of the proposal density that takes into account the complete state sequence. The form is given by this equation. This density can be written like this. The idea over here is to split the state sequence into two parts. This is the first part, and this is the second part. Next, we can use this probability rule to transform our density. After the transformation, we obtain this equation over here. Since the proposal density is not strictly related to our dynamical system, the Markov property does not hold by default. However, we can always make an assumption that is similar to the Markov property. Consequently, we can assume that this density over here can be written like this. Next, let's transform this density. The first thing that we need to observe is that this density should not depend on the output at the time instant k. Also, this density should not depend on the input at the time instant k minus 1. This is because from the state equation of our state space model, it follows that the last state in this sequence, that is the state xk minus 1, does not depend on the input uk minus 1. Instead, the state xk minus 1 depends on the input at the time instant k minus 2. Consequently, we can write this density like this. Now, let's substitute this equation and this equation in this equation. And as the result, we obtain this equation. This equation is very important. From this equation, we can observe that the smoothed proposal density, that is this part over here, depends on its value at the time step k minus 1. That is, it depends on this part over here. This important conclusion and derivation enables us to develop a recursive relation for the weight wk tilde, and consequently for the weight wk. Let's see how to do that. The weight wk tilde is given by this equation. It's equal to the ratio of the smoothed posterior density and the smoothed proposal density. By substituting the recursive equations for these two densities in this equation, we obtain this equation over here. Next, we can group this term over here and this term over here together to obtain this fraction, and the remaining part is given over here. This last term is actually the value of the weight of the smoothed posterior density at the time step k minus 1. That is, this part over here is equal to wk minus 1 tilde. By substituting this equation in this equation, we obtain this very important equation. By using this equation, we can recursively compute the weights wk tilde. Here, it's very important to observe the following. We can compute the weight wk tilde without knowing the full state trajectory x from 0 to k minus 1, or the previous input trajectory u from 0 to k minus 2. The information that is necessary to compute the weight is stored in the vector yk, in the vector xk, in the vector xk minus 1, in the vector uk minus 1, and in this weight wk minus 1 tilde. Due to this, from this equation, it follows that the importance weight wk of the original posterior density, denoted like this, satisfies this equation. That is, wk is proportional to the term on the right hand side. This symbol over here is the proportionality symbol that is often used in probability and statistics to denote that a distribution or a quantity is proportional to another one. Here we use the proportionality symbol instead of the equality symbol. This is done since we need to introduce a normalization factor that will ensure that all the weights computed by using the right hand side sum up to 1. In practice, we first compute the right hand side, given over here, and then we normalize these computed quantities to obtain wk with the index psi. This will be explained in more detail in the sequel. Now that we know how the weights should be computed in the recursive manner, we need to address the following problem. We can observe that in order to compute the weight given by this equation, we need to know this density q over here. So how to select this function? Here is the idea. The idea is to select this function such that, number one, we can easily draw samples from the distribution corresponding to this density, and number two, the expression for the weight significantly simplifies. So how to select this function q? One of the simplest possible particle filters, called the bootstrap particle filter or the sequential importance resampling or SIR filter, selects this function as the state transition density. That is, it selects this function according to this equation. Now, if we substitute this equation in the equation 40, that is in the equation for the weight, we finally obtain this equation. From this equation, we can see that the weight wk should be proportional to the measurement density multiplying the weight at the time instant k minus 1. This implies that for the state sample xk with the index psi, the weight wk with the index psi is computed by using this equation. That is, the weight is computed by using the previous value of the weight and the value of the measurement density at the state sample xki. Also, after we compute the right hand side, this right hand side should be normalized, so keep in mind that. Here, it should be kept in mind that the samples xk with the index psi should be sampled from the distribution with the density given by this equation. That is, they should be sampled from the state transition probability. The computed weights and the state samples are used to approximate the posterior distribution given by the equation number 5, that is, given by this equation. Now we are ready to formulate the particle filter algorithm. First, we will state the algorithm and then we provide detailed comments about every step of the algorithm. Here is the statement of the SIR or bootstrap particle filter algorithm. For the initial set of particles given by this set, we need to perform the following steps for k is equal to 1, 2, 3, 4, etc. Step 1. Using the state samples xk minus 1 with the index I computed at the previous step k minus 1, at the time step k, generate n state samples xk with the index I from the state transition probability. Step 2. By using the observed output at the time step k, that is yk, and the weight wk minus 1 with the index I computed at the previous time step k minus 1, calculate the intermediate weight update denoted by wk with the index I and with a hat by using the density function of the measurement probability, that is by using this equation. After all the intermediate weights are computed by using this equation, we compute the final form of the normalized weights wk with the index I like this. We simply take the sum of all the intermediate weights and we divide the intermediate weights with the sum. And that's it. That's called normalization in statistics. After step 1 and step 2, we computed the set of particles for the time step k, given by this equation. Step number 3. This is a resampling step that is performed only if the condition stated below is satisfied. Namely, we first compute the constant n effective. N effective is given by this equation. If n effective is smaller than n over 3, then we generate a new set of n particles from the computed set of particles in the step 1 or 2. That is, we take the computed set of particles, which we call the old set, and we resample particles from this set to compute a new set of particles. To perform resampling, we will use a special method, and more about this method in my next tutorial. That is in the third tutorial part. Again, in this equation, the old set of particles is the set of particles computed after step 1 and step 2. That is, this is the set given over here. Here's the explanation of the algorithm. We initialize the algorithm with the initial set of particles given in this equation. This set of particles can be obtained by generating initial state samples from some distribution that covers the expected range of initial states and by computing the weights. For example, we can assume a uniform distribution and we can assign equal weights to all the points generated from a uniform distribution. In step 1 of the algorithm, for the given value of the state sample xk minus y with the index I that is computed at the previous time k minus 1, that is at the previous step of the algorithm, and for the given input value uk minus 1, we generate a state sample xk with the index I from the state transition distribution. As explained in our previous tutorial, this step consists of generating a sample of a process noise vector in our state space model given by the equation 1. That is, we simply generate a process noise, that is, we sample a process noise from a distribution describing the process noise, and we compute xk by using this equation. Simple as that. In step 2 of the algorithm, we first compute intermediate or not normalized weights given by this equation. To do that, we use the weights from the previous time step and the value of the measurement density that is computed for the current output measurement yk and the state sample xk with index I. This state sample is actually generated in step 1 of the algorithm. After we compute all the intermediate weights, we simply normalize them to compute the weights wk with the index I. In step 3 of the algorithm, if this condition is satisfied, then we need to resample our particles. Here is the main reason for resampling. Namely, it often happens that after several iterations of the particle filter algorithm, we will have one or only a few particles with non-negligible weights. This means that most of the weights of the particles will have a very small value. Effectively, this means that the weights of these particles are equal to 0. This is the so-called degeneracy problem in particle filtering. Since the time propagation of every particle consumes computational resources, we waste computational resources by propagating particles with very small weights. One of the most effective approaches to deal with the degeneracy problem is to resample particles. This means that we generate a new set of n particles from our old set of particles, and that's precisely this step. We will thoroughly explain two resampling approaches in the third part of this tutorial. One of the approaches for selecting particles from the original particle set is based on selecting n state samples with replacements from the original set. The probability of selecting the sample xk with the index I is proportional to its weight, wk with the index I, in the old particle set. That is, we draw samples from the probability whose density is actually an approximation of the posterior density at the time step k. After we draw samples, we set their weights to 1 over n. That is, we reset the weights. Okay, this would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. And see you in the next video tutorial.